Hey everyone, and welcome back to The Explainer. I am absolutely thrilled you're joining us today because we are going to move way beyond the typical tech buzzwords. We constantly hear about the cloud and digital transformation, but today we're going to literally dissect the physical hardware that makes the Internet of Things actually possible. We're going to break down the physical anatomy of a thing and look at the exact structures and pathways that bring our physical world online.
Okay, let's dive right into this because the sheer scale of this network is it's mind-blowing. Experts forecast that by the year 2020, there were already a projected 50 billion connected devices, or things, communicating across the internet. 50 billion. I mean, put that into perspective, that is vastly more than the entire human population. It creates this massive invisible web of constant chatter going on all around us.
So, here's our blueprint for today. First, we'll cover what IoT things actually are. Second, we'll peek inside an IoT device. Third, we'll outline the 4 protocol layers. And finally, we'll spend some time exploring the link layer. All right, section 1. What are IoT things? Let's figure out the absolute baseline unit of this massive network. We toss the acronym IoT around all the time, right? But I want to ask you directly, what exactly gives a piece of hardware its own distinct thing identity? Like, what transforms a plain old simple object into an autonomous participant in the digital realm? Well, in the context of IoT, a thing isn't just a dumb object. It's a device equipped with a completely unique identity, and it acts almost like a digital nervous system. It has the ability to sense its environment, actuate or make physical changes, monitor conditions, and communicate with other connected devices. And depending on things like its memory, processing power, or communication speed, it might process all that data locally, or send it up to centralized servers in the cloud to be crunched there. And this brilliantly illustrates the sheer variety out there. We aren't just talking about smart home appliances or, your smart fridge. We are looking at wearable health sensors, smartwatches, heavy industrial machines in factories, automated automobiles, and smart lighting systems. Literally, every single node on this network is an active, talking participant in the Internet of Things. Moving on to section 2, inside an IoT device. Now we're going to perform a little teardown and look under the hood of these connected machines. Take a look at this. This is the foundational blueprint of almost every IoT device out there. You've got the processor in the center, that's the brain, and surrounding it are the various interfaces that allow it to actually interact with the physical and digital worlds. Whether it's a smart thermostat on your wall or some massive industrial sensor, they all basically share this generic internal architecture. Let's break that down a bit further by treating these interfaces almost like biological organs. You have memory and storage interfaces kind of acting like the device's hippocampus to retain data. You have internet connectivity interfaces acting as the vocal cords to communicate out, audio and video interfaces if it needs to output media, and crucially, you have the sensor interfaces, which let it interact physically with its surroundings. Those sensor interfaces are absolutely critical. Think of them like the device's 5 senses. They collect data from onboard or attached sensors. We're talking temperature sensors, humidity sensors, light intensity sensors, and they're constantly translating that raw environmental data into a continuous stream of digital information. All right, section 3, the 4 protocol layers. Now that our device is physically built, we really need to understand how it actually talks to the outside world. IoT communication is highly organized into a stack of 4 distinct layers: the link layer, the network or internet layer, the transport layer, and the application layer. It's a whole chain of command. But for this explainer, we are going to focus our microscope specifically on the very bottom foundation of that stack, the link layer. Which brings us to section 4, exploring the link layer. Get ready because we're going to do a rapid-fire roll call of the physical mediums that actually carry our data. So the crucial point here is that the link layer is the literal physical bridge between the device's hardware and the local network itself. It determines how those digital packets of ones and zeros are actually transmitted. We're talking about electrical pulses traveling over copper wires, flashes of light zipping through optical fibers, or invisible radio waves bouncing through the air. First up in the link layer is 802.3 Ethernet. This is your heavy-duty wired workhorse. It supports communication through coax cables, twisted copper pairs, or optical fibers. And because it's hardwired, it is incredibly fast, providing data rates starting from 10 megabits per second all the way up to a massive 40 gigabits per second and beyond. Next is the one we literally all know and rely on,
802.11 Wi-Fi. This is the family of wireless local area network standards. So instead of wires, it uses those familiar, invisible radio waves bouncing around our homes and offices, operating on frequency bands like 2.4 gigahertz and 5 gigahertz to connect our devices.
Then we've got 802.16, known as WiMAX. Think of this as the heavy-hitting wireless broadband solution. When you need to cover a much wider geographic area than a standard Wi-Fi router can handle, WiMAX steps in, providing high-speed data rates from about 1.5 megabits all the way up to 1 gigabit per second. But hey, what if you have a tiny little sensor running on a cheap coin cell battery? That's where 802.15.4 LRWPAN comes in. That stands for Low-Rate Wireless Personal Area Network. It's perfectly tailored for low-cost, low-power devices, forming the foundation for tech like Zigbee. It provides just enough speed, up to about 250 kilobits per second, to do the job without killing the battery. And finally, we absolutely can't forget cellular technologies: 2G, 3G, and 4G mobile communications. When an IoT device, like a car, needs to physically leave the local network and go on the move, it relies on these generations of cellular tech, like GSM, CDMA, and LTE, to stay wirelessly connected to the internet from virtually anywhere.
Now, what's really interesting about this slide is how it clearly shows that form absolutely follows function. A smart thermostat relies on a tiny 250 kilobit per second Zigbee connection because it just needs to send tiny bursts of data and save power. But a massive central server, it requires the huge 40 gigabit pipeline of a wired Ethernet connection.
As we wrap up, I want to bring the hardware and these protocols together with a perfect quote from our source material. Most IoT devices generate data continuously. When analyzed, this data produces useful information that helps in decision-making. All of this physical infrastructure exists for one sole purpose: to take raw data from our world, move it, and turn it into smarter local and remote automation. Which leaves us with a final, fascinating question to ponder. We've seen how these devices are built and exactly how they speak. But what actually happens to our society, our cities, and our daily lives when every single physical object around you has a continuous digital voice? Thank you so much for joining me on The Explainer today. Keep exploring, keep questioning, and I'll see you next time as we continue to unpack the incredible systems that run our world.